in our lecture, there will be one important class of posets, and this is our posets that satisfies ascending chain condition. That means there are no infinite ascending chains. So if chains go up, 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 it has to stop after finitely many steps. And of course, every finite ordered set satisfies ACC. And what will be our outcomes? It will be anti-chains. That means these are non-empty sets that have all of the elements of them are mutually incomparable. So there are maximum values in some sense. We need the notion of a Laver set, which is a set Y such that all elements that lie between, under some element of Y are in Y. So that are Laver sets. And we all will assume that it will always be non-empty. And it is clear that if we take a system of all Laver sets, it's a complete lattice, and it is, of course, ordered by inclusion. For each poset Y, we denote by Y the set of all maximal elements of Y. And if we assume that our posets satisfy ACC, that means that every Laver set can be defined as a Laver set of some anti-chain. So there is one-to-one connection between anti-chains and Laver sets. Of course, only for posets satisfying ACC. And that means that we can have the lattice of our anti-chains where the order, the two anti-chains are in relation less or equal, if and only if the respective Laver sets generated by them satisfy the inclusion relation. Yeah? So the key property we will use in our lecture is that down sets or Laver sets correspond one-to-one to anti-chains. So we can work very easily with them. Let me come to some easy motivation. Here is a classic lattice N5, which is non-modular. So that means it cannot be residuated in classical sense. But as we can show later, it will satisfy so-called unsharp adjointies. In fact, we can define implication in this way, the classical one, only this result, that C implies A, will be two-valued outcome, A and B. And with respect to this implication, it will be satisfied the adjointing condition. So let me be more precise. Having some ordered set, say A with ACC, and taking two elements AB, and let us define multiplication A times B as the set of all maximal elements of the Laver set generated as an intersection of LA and B. This is, of course, again a Laver set, so we know the maximal elements exist and are uniquely determined. Similarly, we can define implication as the set of maximal elements of this Laver set. And the results are always anti-chains, not single elements. Yeah, it will be single elements if we are happy, but generally the result will be anti-chains. And such an operation satisfies many nice properties. For example, we have unit, which is this anti-chain. The operation is commutative. Operation is associative. Is order preserving in each variable, and multiplying with the anti-chain, with the one element anti-chain generated by zero element, we get always zero. Yeah. So all you know that these are zero tenor properties. Yeah, so that's quite nice. And what we were able to show that really the adjointness condition, which is valid in residuated lattices, is valid also in this setting. So that means our lattice of antichains forms a complete Heyting algebra. And in fact, our operation is the same as mean with respect to the order I have introduced before. This is the classical Heyting algebra implication. And as said before, every finite poset generates unsharp residuated structure. So, but we would like to have more, not only Heyting algebras, we would like a more diversified structures. So let me start what a uniposet is. It's a bounded poset, and we have multiplication that prescribes to two element some Laver set. Yeah, and we ask that this operation is order preserving, and zero will be the zero element. So this will be our structure for a moment, and we define what a binary subalgebra will be. It will be a complete lattice Q with this operation. It will have a multiplication, binary operation, and we ask only that this operation distributes over arbitrary joints. And what's important is that whenever we have a uniposet and form the lattice of all Laver sets with respect to the union and multiplication defined as here below, we get a binary subalgebra. My favorite structures are quantas, which are in fact complete residuated lattices. And in case if this operation will be associative, the resulting structure will be a quantal. So this is the connection with facet set theory. And this prescription is categorically very nice. It's a reflection from the big category of uniposets into a smaller subcategory of binary subalgebras. The reflection is monoreflective, but not epireflective, but that's not important for the talk. And because I'm coming from Maastricht University, which is called MUNI, so I introduced MUNI-poset. And it will be on bounded posets with ACC, and the multiplication prescribes to two elements for our poset some subset of some antichain. Yeah. And the only thing I ask that this operation will be order preserving and zero will be zero element. And the same results I presented slide before are valid for our antichains conditions. Yeah, we will get a relation. This lattice will be binary subalgebra, and we get a reflector. Let me give you some example. This is very trivial poset. We have only maximal elements and smallest one. What will be the antichains of it? It will be the atomic Boolean algebras. In fact, subset algebras in some sense. The other example, yeah, we have a lattice M3, which is modular but non-distributive, and we can define multiplication of sharp in this way, but this will be not a uniposet because our relation is not order preserving. You see that if we multiply A times C, we get B, and n times 1 is AC, but B is not under AC. So we have to be careful which multiplication we would like to introduce. So let me give you summary of my talk, we introduce unsharp operators for poset with ACC. We have there this unsharp and this condition. In a special case, this will be always complete Boolean algebra. We introduce categorical theoretical framework as well in the solution, and we provided some nice examples. So that's, I think, all, because we have to be in time for the question. If there are some, the paper was already published, and thank you for your attention.
Thank you very much for your talk. Perfectly on time. We have 5 minutes for discussion. Some questions, remarks.
Yeah.
Your construction reminds me something that we have been working some 10 years ago or something about multi-lattices, reciprocated multilattices. So I don't think if they are exactly the same structure, but for sure
there's a similar structure because you have hyper structures which were studied by similar. But the special thing is that we have chosen a special kind of subsets.
Yeah.
Not all ones, but only the anti-chains.
Yeah.
That's the difference.
Okay, so it would be good to try to find some time to discuss.
Thanks.
Thank you very much. Maybe I have one question. I am wondering what anti-chains can represent it from the logical point of view.
So let me, it is something here. So let us look on some poset. It will be finite one because I have finite many times to do it. Something. That's a poset. It has no upper element. As you can see. And you have, for example, this anti-chain. This is a kind of minimal value of information. If you think of this, you have. I will give it something here because I would like to a little bit cheat. So that's and that's. So you see that you have no upper bound here of these two elements of information. So it's clear that the information about this point is not complete. And about this as well. So you see that your logic or your information system is not one complete, so you have to, in fact, enlarge it to get the complete one. And the complete one you get using this anti-chains. If you construct the anti-chain, it will be a complete lattice, and there will be a complete information about anything.
Okay, so it means that this is like the set of some
you make
possibilities,
in fact, very trivial completion of a poset, finite poset. And that's the complete information, and you can extend your T-norm or something, this uninorm or uninorm on the whole thing. And you get something which is similar to T-norm.
Okay, so thanks once again. We can slowly continue to the second talk. The second talk will be provided by Jakub Rumbieś, and the title is Admissible Pairs of Quasi-Linear Means and Related Families. Please, Jakub, take the floor.
Thank you. Okay, so good afternoon, ladies and gentlemen. My name is Jakub Rumbieś. I'm from Poland, and today I would like to talk about admissible pairs of quasi-linear means and related families. So the presentation consists of these 5 points, and I would like to briefly talk about motivation behind choosing that topic. Later, I would like to recall some basic notions that were used during the research. And later, I would like to explain those families that are related to quasi-linear means, and also give some general results as well as particular examples. And lastly, I would like to talk about possible directions for our future. So the motivation, and the motivation behind this topic is that we have seen that there are some recent constructions, as you can see on the presentation frame, the papers. There are some recent constructions on new admissible orders, and we've also noticed that. No. Okay. We've also noticed that in the whole class of the admissible orders that are generated by admissible pairs of aggregation functions, probably the mostly known and widely applied admissible order is the order generated by weighted means with distinct weights, also known as the alpha beta order. And we've also noticed that those newly constructed admissible orders could aid us in creating new interval-valued operators. For example, interval-valued aggregation functions, interval-valued negations, interval-valued similarity or dissimilarity measures, or interval-valued Erf-Scheffer strokes. So with newly constructed orders, we could construct possibly new interval-valued operators. So let us begin with some recalls on the basics. And during this presentation, I will mainly and probably only talk about interval-valued data. So we consider the set of all closed subintervals endowed with the natural partial order, the product order. And in many cases, there is a need to refine this order, this partial order, because we cannot compare every interval input. So in 2013, in the work of Bustins and others, the notion of an admissible order was an admissible order on the set of all closed subintervals of the unit interval was introduced. And basically, this admissible order is a linear extension of a partial order on a given set. Here we have the set of all closed subintervals, and the partial order is the product order. So we also use in the research, we also use the well-known notion of an aggregation function. And in the, as you can see, in the classical definition of an aggregation function, aggregation is defined on the unit square. And here we are using the definition on the set of all closed subintervals. And it's due to the fact that, well, when dealing with interval value data, we don't actually use the whole unit square. We only use the upper unit triangle. And so that's the reason that we've introduced it this way in our work. And as you can see, we haven't changed, for simplicity, we haven't changed the notation because we still are using the notation as it would be on the numbers from the unit square. And it's still okay because there exists a natural bijection between the set of all closed subintervals and the upper unit triangle. And these notions of aggregation functions were also used in the 2013 in the work of Bustins, and the authors introduced the relation that is generated by a pair of aggregation functions. The authors also introduced the concept of an admissible pair, and basically an admissible pair of aggregation functions is a pair that is generating an admissible order from the previous relation that was on the presentation. And the authors also characterized these admissible pairs by, I would like to call it some admissibility condition that will later come in handy. And we can, thanks to this condition, we can get some nice analytical approach to finding those new pairs. And well, I think the standard example of an admissible pair is exactly the admissible pair of weighted means that generates the alpha beta order. As well, the authors also analyzed it thoroughly in their work in 2013. And now that we have our admissible pairs, we can ask ourselves the first question: can we go beyond those admissible pairs of weighted means? Can we construct maybe new admissible pairs of aggregation functions that could generate possibly some new admissible orders? And well, we've noticed that for some certain families of function, here they are in the literature they are known as quasi-linear type functions. We've noticed that this so-called admissibility condition becomes more approachable by some analytical tools. And here, this family consists of classes such as quasi-linear means, strict Archimedean T-norms, including Archimedean copulas, strict Archimedean T-conorms, and these last two classes could be summed up neatly by the class of representable uninorms. And in particular, those classes, we introduced in our research some general results. And well, the theorem is quite technical and quite a lot of text. So this is like the general result, and I would like to go into detail in some particular examples. And here, well, I've chosen some. Firstly, you can see the first two examples are the admissible pairs of some weighted power means, as well as in the second row we have here defined. We have the weighted geometric means. And what is interesting is that when weights are equal, we've obtained full characterization. So these conditions are necessary and sufficient. However, in the case when the weights are different, well, then we have only obtained the sufficient conditions, and we cannot reverse the implication because we can find examples of some functions that the implication does not hold in reverse. And as you can see, those parameters in the conditions, they are produced by the monotonicity conditions as well as convexity conditions that are applied to the generator functions of those quasi-linear type functions. But these conditions are not the only ones that matter when working with these admissible pairs of quasi-linear type functions. We also have to remember that important are the values on the bounds, like here. The values on the bounds are also important, and mainly we cannot have infinities on the bounds. So this result is general, but here to provide an example, a better example, where we have the pair of weighted geometric means, and well, they are generated by the logarithmic function, and we know that when the arguments tend to 0, both logarithmic functions tend to minus infinity. And this is a problem for us because this gives us that this pair is not an admissible pair of aggregation functions. Well, we also have last 2 rows. We also have some arithmetic means that are generated by some finite function, and in this case, it is also necessary and sufficient condition. And we also have the admissible pair of strict Archimedean T-norms and strict Archimedean T-conorms. And this characterization here is also complete, necessary, and sufficient conditions. And we can also show that whenever T-norm here or T-conorm here are nilpotent, then they do not form an admissible pair of aggregation functions. And together with the results from Gupta from the year 2023, we have obtained the full characterization in the class of Archimedean T-norms and T-conorms. So now that we have some new admissible pairs, we can ask ourselves a second question, is that are we able to identify some admissible pairs that the orders they produce won't coincide with the order that is generated by a pair of weighted means with distinct weights? So the short answer is yes. And the more detailed one is that we can do it for any parameter alpha. And the admissible pair exists. And for example, it takes the form like here shown on the presentation frame. And for alpha less or equal than a half, f, the generator f has to be strictly convex. And when the parameter alpha is greater or equal than a half, the generator has to be strictly concave, and then we can find an admissible pair that generates the ranking that differs from the one generated by alpha beta order. And for future directions of our research, well, the first one that we are currently working on are some new constructions with those newly given admissible pairs, some new constructions of interval valued aggregation functions, following the work of the papers presented here. And the second possible direction is the analysis of coincidence between the admissible order generated by those newly obtained pairs with the coincidence with alpha beta order, following the work that was in the 2013 paper by Pustins and others. Thank you sincerely for your attention. If you have any questions, please ask away. If not, you could also contact us by the information provided on the presentation frame. And I would like to also add that this presentation is based on an article that is currently under review. Thank you again very much.
Thank you very much. There are some questions, remarks. We have 7 minutes for discussion. Maybe I have one. If I consider admissible pairs, for example, alpha, beta, and the ordering which is related to this pair, I think that there are 2 different pairs of parameters which generate the same ordering. So you can have alpha and beta and another alpha prime, beta prime, and you get different betas and alphas, and you get the identical ordering. Is it true or not? I think that this is true.
Yes, I think it was also considered.
And there are some properties on alpha and beta, and even on some A and B, that you can generate the class or some equivalence on the set of these parameters, that this class of equivalent parameters generate the same ordering, so that say if you have some alpha beta, so you generate one ordering. Now you say, I would like to have another one, so I choose another one, but you generate the same ordering. So there is some like classification of these admissible pairs to get different orderings on the set of all intervals.
Well, I've known only the ones that you have mentioned for the alpha beta, and well, I think it's the whole analysis, probably the whole analysis that like right now maybe needs to be addressed, because we've only in this research here we've only shown some admissible pairs that satisfy the admissibility condition, but we did not tackle the problem that I think you asked about, because that's like for future research, the determining the equivalence between those.
Because the interesting question for me is how many orderings I can get using admissible pairs. Infinitely many, or so
I know.
Some relationship between the set of all orderings generated by these admissible parameters, and if there is somehow like equivalence on these pairs, that for 2 pairs we get the same ordering. That was my initial question. So I think that there exists something like this, but probably we can get infinitely many orderings using these admissible pairs. But maybe it would be nice for studying this. And moreover, you consider A and B, another type of, say, operations based on this. Maybe also for such type of parameters, you can get the same ordering, and maybe some classification for this ordering could be also helpful.
Okay, thank you for your
okay. Some other questions or remarks? If not, so thanks once again, and we will continue with the next talk. The title is on aggregation of omega groups and fuzzy subgroups, and
perfect.
And the speaker is Ivana. So Ivana, take the floor, please.
Thank you. Okay, so, Hello to everyone. It's really nice to be here in Liptovsky again. It's always a very nice atmosphere and very nice people and some old faces, some new faces. It's really fun to be here. So today I will present you a joint work with my colleague from Department of Mathematics, Andrete Papčević. Unfortunately, she was not able to come here, and I'm really sorry about it because this is, well, to be honest, her cup of tea. You know, I'm all about integrals and measures, so actually it's perfect. This cooperation with her made me brush up on my algebraic structures. Especially I like these omega groups because this construction, the flow of construction is, well, perfect. It goes from one step to another step to another step, and then you get a whole picture. So I found it very, very, very interesting. So motivation. Aggregation operators, yeah, because when you work with aggregation operators, idea is to have input values. You do something with those input values and get one output value. We would love to know to predict the structure of this output value. We would love to have the same structure of the output value as the input values. That would be absolutely perfect. So the idea was, let's see what kind of aggregation operators can help us to maintain this structure if we work with fuzzy groups and these omega groups. So what can we expect from aggregation operators in order to get, as a result, another omega group, or as a result, another fuzzy group? When we talk about aggregation operators, here we are observing aggregation operators. Of course, we need complete lattices here. And this is just the basic idea of an aggregation operator. It has to be monotone. Of course, bigger value, the biggest value have to, okay, where is this? Okay, the biggest value will provide the biggest value, the smallest value will provide the smallest value. Of course, if we have only one input, it has to maintain this input. It's, you know, standard aggregation operator, but now observe complete lattice. And in order to get to this n-ary aggregation operators that will help us, we need some basic algebraic notions. So just a little bit to brush up on those. First, we will observe algebraic structure, one binary operation, one unary operation, one nuller operation, constant. Of course, congruence, we will need those equivalence relations that are compatible with all operations. Just for 1 second here, we have this property. Actually, it follows from reflexivity, sorry. Actually, it follows from reflexivity, but you know, if we observe a weak reflexivity, which means that we want for E to be sure that only this is fulfilled. I don't know about other axes, maybe yes, maybe no, but for E, this has to be. Then we have weak congruences, and a little bit later, we will have to do something with the family of all weak congruences. And what is very nice, this family of all weak congruences is actually algebraic lattice under inclusion. So here is the reference to that. Now, here is this flow of construction, how to get to this omega group. It goes step by step. First, yes, of course, we need a set, we need a complete lattice, greatest element, least element, perfect. And of course, here is a lattice valued relation. But we don't want any kind of lattice valued relation. We want lattice valued weak equivalence, which means that this relation has to be symmetric and transitive. That's enough. And then we have this lattice valued weak equivalence relation. Then next step, let's use this lattice valued weak equivalence and get lattice valued equality. This is how. Complete lattice, algebraic structure, lattice valued relation. Now, if this E is lattice valued weak equivalence that fulfills these conditions here, nothing unusual, just compatible with all operations, then we have this lattice valued equality. Perfect. Now we have lattice valued equality, and we are coming to the last step. we are coming to this omega group. So omega group is actually an ordered pair where we have this algebraic structure. As you can see, it's just an algebraic structure. Later on, we will comment what if it's a group. So for now, it's enough that it's an algebraic structure with one binary, one unary, and one nullary element. And this E is lattice valued equality. And we want this E to satisfy these additional conditions. Somehow this E will actually do a little bit grouping of this structure. Oh, sorry. Of this structure here. And if we have all these conditions fulfilled, we can say that ordered pair is our omega group. Perfect. What is especially interesting? If we work on a group, if we start not just with an algebraic structure, but with a group, then this all presents no problem whatsoever. So this pair is an omega group for any lattice valued equality, which is very nice property. Another thing that is very interesting when we talk about omega groups is that from omega group, we can go to omega valued sets. Omega valued set, we will use this E and we will construct mapping that ends up in omega. That's why it's omega valued set. And it's done like this. Actually, this is lattice valued fuzzy set. So this is actually a membership function for a lattice valued fuzzy set. And it follows very easily from all these previous conditions that are needed that something like this is fulfilled, which means that we are getting to fuzzy subalgebras. Actually, we are getting to fuzzy subgroups if this is a group. So perfect. We have both omega groups and we have those fuzzy subalgebras in, so to say, in one package. Okay, since I already have too many slides, I think I can skip this one and I can skip this one. Okay, let's go to aggregation operators. Again, aggregation operators on lattices. We've already discussed what that means. What is especially interesting, what will be proved to be very useful while dealing with this problem of preserving structure is compatibility with congruences for our aggregation operator, and this notion of weighted lattice polynomial. Actually, this notion of weighted lattice polynomial is what convinced me that, okay, I would like to see this, because something is hidden here, something that is pretty much in my field of interest, so to say. So let's see first this compatible with congruence on omega. If we have a congruence relation on, if we have congruence relation on lattice, and aggregation operator is compatible with this congruence relation, if something like this holds, which means what? If our input values are in this relation, output value has to be in this relation. Okay, if we say that it is compatible on omega, it means that it's compatible with all congruences on this omega. Very nice property. And just a little jump, I will go back. So weighted lattice polynomial, just very, very quickly, I'm sure you all are familiar with those. Definition is inductive if E, so each variable x is weighted lattice polynomial, each constant is weighted lattice polynomial. Then if we have two weighted lattice polynomials meet and joined, is again weighted lattice polynomials, and repeat. And here is what is especially interesting regarding aggregation operators and those weighted lattice polynomials. If we have complete distributive lattice, perfect. A is compatible aggregation operator. It means compatible with all congruences, if and only if it is weighted idempotent to the lattice polynomial function. Very nice connection between aggregation operator and polynomial functions. Perfect. But that's not all. So this is a very nice result from this paper from 2016. There is another very nice result that can be combined with the previous one. So again, omega is complete distributive lattice, and this function is weighted lattice polynomial function if and only if it can be represented in this manner. Of course, we have here option for a binary situation, but it goes for n-ary situation as well. The original theorem is, of course, for n-ary case, but here is only this binary because that's the one we will use a little bit later. This is also very nice. This is very nice result from this paper here, which means that we actually can combine aggregation operators and this form, this representation here. Let me go back. So aggregation operator is weighted idempotent lattice polynomial function, and here we know that weighted lattice polynomial function can be represented in such manner. And now we have the results. First, let's see the general case, only complete lattices, because if I go back here, you see that we have here complete distributive lattices. So first, complete lattices. If we have just complete lattices and we have an aggregation operator on this lattice, then for every algebra, the result of aggregation of omega groups is an omega group if and only if this aggregation operator dominates meet. In other words, this here holds. Proof is a rather long one, but it's pretty much technical. You know, you have to play a little bit with all these algebraic notions. What is the most important part of this proof is that you actually, I'm quite certain that you are already got the idea that you are actually constructing new relation for the resulting omega group by aggregating those input relations with this aggregation operator. So it's very natural way of obtaining this E. So let's go next step. This was, so let's go back. This was general case, just a complete lattice. But if we have complete distributive lattices, then we have something more. This is case for binary aggregation of omega groups for distributive lattices. And first of all, what can we notice? So if omega is completely distributive lattice, a aggregation operator, and if it's of this form here, then you can see that this meet works nicely with our aggregation operator, of course, under a condition if and only if this here holds, which allows us to go back, which allows us to go to this theorem here and to conclude something like this. Again, completely distributive lattice, aggregation operator compatible aggregation operator on omega, such that for every algebra, the result of aggregation of omega groups is again omega group, if and only if our aggregation operator is of this form. We are actually using connection between compatible aggregation operators and weighted lattice polynomials here. Short example, here is one lattice. There is a Klein group. Unary operation is given like, binary operation is given here. Unary operation is given here. So it's not very complicated group. We have two algebras, which means we have two omega groups, which means we need E1 and E2. And let's suppose that they are given like this. And we can aggregate new omega groups from these two. If we follow the previous theorem, aggregation operator should be of this form. There are a couple of options for these aggregation operators, but let's observe only these two for the sake of this example. If we observe this aggregation operator, then we get omega group. Omega group will have this equivalency relation E of the form here. But if we observe this aggregation operator, just slightly different, but it fits in all requirements, we get omega group, this one here, and F would be our equivalence, and here it is. So very, very short example. But what is happening with lattice-valued fuzzy subgroups? We can go back to this slide quickly. No, to this slide, where we can see that omega groups and omega valued sets, actually with fuzzy subgroups, are connected, and that can be used. And it has been used. So if this is omega group, then this mapping is lattice-valued fuzzy subgroup. And first, there is one very, well, it's very nice lemma. That's why I put it here. But the main point is actually this corollary that that follows from all the previous results. So first of all, this lemma, we have a group. Here we have lattice-valued subgroup. Yeah, we know that it has to be now lattice-valued fuzzy subgroup since this is a group, and omega is a lattice. This is complete distributive lattice. No, sorry, this is just a lattice. Then a lattice-valued relation can be defined like this. Now we can obtain, if we use this E, we can obtain an omega group. Based on this lemma, we can subtract this this interesting claim. Omega, a completely distributive lattice, an aggregation operator. As you can see, it's given like this. Then the result of aggregation of lattice-valued fuzzy subgroups by A is again lattice-valued fuzzy subgroup. So this structure is maintained. Now, if we go to n-array aggregation operators, we've only considered one type of n-array aggregation operators. So there is room for further investigation. First of all, it can be shown that aggregation operator of this form is associative. Now, when you see this associative, there is already idea what can we do next. So the theorem is here. A is a previously given binary aggregation operator on distributive lattice. Now we have a new n-array function, n-array operator, that is actually constructed from this aggregation here, which is possible because of associativity. And this, for this new n-array aggregation operator, we have this preservation of structure. The result of aggregation of omega groups by B is again omega group. So only this possibility for n-array aggregation operators were observed for now. And what else is especially interesting, and why this was very interesting for me? Of course, we are talking about lattices, but we can use whole interval 0, 1, and we can go, this is nicely put, the classical fuzzy case. I find it a little bit funny. So, but another thing is connection with discrete Sugeno integral. So here it is, my favorite integral is here. In practical, discrete Sugeno integral, well, you can observe it as a weighted lattice polynomial function. Therefore, those results that we have that are based on weighted lattice polynomial functions actually can work for Sugeno integral, and aggregation of omega group will give us omega group, which is very interesting from my point of view. So very quickly, some references, actually a lot of references, and thank you for your attention.
Thank you very much for interesting talk. Some questions, remarks? No questions, no remarks, maybe.
Slide before the example.
Yes.
I will try. This one?
Yes. Because in the presentation theory by my child,
Yeah,
there was also
the representation.
a fourth, yeah.
Yeah.
There is a fourth constant, A, B, C, and D.
Yeah, oh yeah, you're right.
But why it is not considered there in the theorem? Because it doesn't, it is necessary to avoid D.
Okay, you got me now. I don't know where I've lost the D. Probably in typing. No? I went too quick. Yeah. So there it is. Kalash, that's the one. Oh, there is D. Yeah, that's okay. But here D is missing. Yeah, D is missing. You're right.
Yeah, it should be.
Should be there.
Okay, but this is a detail. Nothing is changed.
So
Okay, so it's very interesting that you combined many results together and you get some new results. But unfortunately, we don't have time to discuss it more. So thanks once again for nice talk. And we are moving to the last talk. The title of this talk is Fuzzy Extensions of Anti-Ideal Structures in Semi-Groups. So now, yeah, online. And who is the speaker? Madeline. Okay.
Good evening.
So the speaker is Madeline. So please take the floor.
Good evening, and thank you for the
Nobody is there?
introduction.
No.
Hello? Hello? Hello, are you able to hear me? Hello? Okay, you're hearing me? Hello? Hello? Good evening. Are you able to hear me?
Yeah. Please, you can speak now. We see your slides, so you can start your presentation.
Hey, good evening again, and thank you for the introduction. It's a pleasure to be here at FSTA 26. This presentation is a joint work
Oh,
with
please,
Sarka.
we don't see you.
Yeah, the
Can hear
camera
you.
is not working on this computer.
Let's try to turn on your camera and microphone.
The microphone is working, right? Are you able to hear me?
No response.
I'm hearing you. Are you hearing me? Hello?
Yeah, now we are hearing.
Okay, perfect. So again, good evening. And this
We
presentation
can see
is
you.
yeah, my
Maybe you
camera
can
is
turn
not
on your
working.
camera.
I'm unable to turn on the camera. It's not working on this computer. This is a joint work with Professor Sarka, which she's probably in the auditorium. And it's a pleasure to be here at FSTA 26 for the second time. In classical semigroup theory, much of the structural insights come from studying closure, idols, filters, and their invariants. Today, I'd like to take the opposite perspective, non-closure, by focusing on anti-idol structures and their fuzzy extensions. Anti-idols capture subsets that deliberately avoid interaction with surrounding semigroup structure. When fuzzified, they provide a natural framework for modeling degrees of isolation. The aim of this talk is twofold. First, to systematically compare anti-idol by anti-idol and interior anti-idol in semigroup. And second, to show that their fuzzy counterpart not only generalize the crisp theory, but recover it exactly through level set. Since this is an expert audience, I will focus on structural insights and conceptual relationship rather than technical proof. Let's get started. So semigroups, as we know, are fundamental algebraic structures defined by an associative binary operation. They generalize groups by relaxing the requirements for identity elements and inverses. This flexibility makes semigroups a powerful tool for modeling a wide range of real-world processes, from computational systems to linguistic patterns. However, analyzing an entire semigroup directly can be complex, and because of that, we focus on specific subsets such as idols, filters, and anti-idols that we will do in this presentation. So we'll start first with the definition of anti-idols. Please, if you have any question at any slide or any idea that you would like to further discuss, please stop me and I will be happy to answer. Schwartz played a pivotal role in advancing anti-idol theory by introducing the concept of anti-idols. Now, how anti-idles were introduced? It's similar to idles, but we need the intersection to be empty. So if you recall together the left idle, what do you mean by it? We can say that A is a left idle if XA is a subset of A. But for anti-idles, we need the intersection between XA and A to be empty. Similarly, the right anti-idle is defined in the same way. And of course, an anti-idle, it will be left anti-idle and right anti-idle. Here are a few examples of anti-idles. If you go to the semigroup of positive integers and define sets or subsets of this form, then we can easily see that these subsets, they are anti-idles of P. Here are some important results on anti-idles. The first thing, that anti-idle, they do happen in semigroups, as we saw in this example, but they cannot happen in monoids. And of course, a monoid is a semigroup that has an identity. And of course, if it doesn't occur in monoids, it will not occur in groups. And if a left and right anti-idle, they are not like idles. Idles, they should be subsemigroups, whereas left and right anti-idles, they are not subsemigroups. And of course, every non-empty subset of an anti-idle is again an anti-idle, and the intersection is an anti-idle as well. We'll next continue by defining bi-anti-idle, interior anti-idle, then we'll leave with a summary of them in order to start with the fuzzy counterpart of each. So if you recall together, what do you mean by bi-idle? Bi-idle is A to be bi-idle, we should have AXA a subset of A. So when we want to define bi-anti-idle, we need this intersection to be empty. And if we look at this example, if we consider again P as the semigroup of positive integers, we will get this subset as a bi-anti-idle. And it's clear that this subset is not a left or right anti-idle. It means that if I have a bi-anti-idle, it's not necessarily to be a left or right anti-idle. So these definitions, they intersect at a certain point, but they are not equivalent to each other. And when I say intersect, it means that it's one way only. So every left or right anti-idle, it will be a bi-anti-idle, but the converse will not be true. And again, a subset of a bi-anti-idle, if it's non-empty, it will be again a bi-anti-idle. And of course, it's not a subsemigroup. Now, the interesting thing about bi-anti-idles, if we recall together that anti-idles do not occur in monoids. However, in monoid, we might have a bi-anti-idle. So if we consider the monoid of non-negative integers under standard addition of integers, if we look at this set, it will be a bi-anti-idle of it. And it's clearly seen by this one. And of course, as the union of idles is not necessarily to be idle, so here the same, the union of bi-anti-idles is not necessarily to be an anti-idle again, and here we have a counterexample. Here we define the interior anti-idles similar to defining the interior idles. So if you recall again together, what do you mean by interior idle? A is an interior idle of X. If X, AX is subset of A. So for interior anti-idle, we need this intersection to be empty. Here we have an example of interior anti-idle. And again, this is an interior anti-idle, but it's not a left anti-idle nor right anti-idle. This is an example of interior anti-idle as a real life example. And here again, we have some interesting results about interior anti-idles. They do not occur in monoids, and of course, they will not occur in groups. The subset of an interior anti-idle is again an interior anti-idle, and the intersection is also interior anti-idle if it's non-empty. Regarding the union, again, it's not necessarily to be an interior anti-idle, and this is a summary of the anti-idles together. So this is the definition of anti-idle, by anti-idle and interior anti-idle. Now, if we have an anti-idle, it means that it's by anti-idle, but the converse is not true. Whereas for interior anti-idle, they are independent. All of them cannot be sub-semigroup. We have closure under subsets, closure under intersection, closure under union. It doesn't occur in any of them. The existence in monoids, it's just for bi-anti-idles, whereas in groups, it doesn't exist for any of them. Next, we are ready to introduce the fuzzy counterpart of these concepts, and we'll start with the fuzzy anti-idle. So if we have a semigroup and mu as a fuzzy subset of it, then this mu, we consider it as fuzzy left anti-idle if we have this one is satisfied. And by this, we mean the minimum between mu r a and mu a, it should be 0. For right anti-idle is defined the same, and fuzzy anti-idle, it should be left, and fuzzy right at the same time. Here's an example on fuzzy anti-idle. If we consider again the semigroup of positive integer and define it in this way, where mu k is 0.7 if k only 1 and otherwise it's 0, we can easily see that it's a fuzzy anti-idle of P. Here's the definition of fuzzy bi-anti-idle, and we are providing an example that is fuzzy bi-anti-idle, but it's not a fuzzy anti-idle. So the fuzzy anti-idle is a fuzzy bi-anti-idle, but the converse is not true, and this is a typical counterexample for it. And here's the definition of fuzzy interior anti-idle, and again, we have here an example on it. Also here, we are considering a finite semigroup, and we are defining an example of it where we have mu as a fuzzy interior anti-idle. In this presentation, we will present the results for the case of fuzzy interior anti-idle for the sake of time, and the others are done similarly. So if we started with X as a semigroup, and we are starting with two non-zero fuzzy sets of it, if mu1 and mu2 are, one of them at least is a fuzzy interior anti-idle, then their intersection as well is a fuzzy interior anti-idle, and the proof is almost straightforward. Here we are defining the level set, and the level sets are very important in the theory of fuzzy algebraic structures because they connect the algebraic structures with the fuzzy part of them. So here we find a relationship between interior anti-idles and fuzzy interior anti-idle, and this relationship is found through the level sets. So we have mu a fuzzy interior anti-idle of X if and only if mu t, the level set, is either the empty set or an interior anti-idle of X. And we can characterize the interior idles, we can represent them as level set of a fuzzy interior anti-idle. This one, it reminds us of representing every idle or every interior idle of a semigroup as a level set of a fuzzy interior idle or idle of X. Let me conclude by briefly summarizing the main message of this work. We examined three classes of anti-idle structures: anti-idles, bi-anti-idles, and interior anti-idles, and highlighted how each captures a different form of resistance to the semigroup operation. By introducing fuzzy versions of these concepts, we showed that fuzzification does not merely weaken classical notions, but instead it provides a unifying framework in which crisp anti-ideals appear naturally as level sets. From broader perspectives, this work opens several directions. We can have detailed investigation of additional structural properties of fuzzy anti-ideals and, of course, interior anti-ideals by anti-ideals. We can extend fuzzy anti-ideal theory to broader algebraic systems such as hypercompositional algebra, or maybe to rings, modules as well. And we can have development of applications-oriented models illustrating the usefulness of fuzzy anti-ideal concepts in real-world problems. Here are a few references. And thank you for your attention. I look forward to your questions and comments.
Thank you very much for an interesting talk. There are some questions or remarks. No, maybe I have one. So you consider anti-ideal for some algebraic structure. So
Yes.
this is like a dual poem to ideal there, because or this is completely different story.
Now, the anti-ideal is not a new idea. It was introduced by Schwarz. Let me just make sure that I believe that I put the... Okay. So the anti-ideal was introduced already by Schwarz. Then the new ideas that we had, he introduced the anti-ideals and not the fuzzy anti-ideals. So the fuzzy anti-ideal, it was new. This one was already introduced by Schwarz. The fuzzy anti-ideals, we worked on it. And what was new is we introduced the interior anti-ideals and the bi-anti-ideals. Did I answer your question?
Yeah, thank you. So now I am thinking about the interpretation of these anti-ideals in practice. What does it mean? Because I can imagine what anti-ideal like filter in the standard theory means, but what is the interpretation, some like logic behind this concept? Why we should be interested in this anti-ideal of some X for some semi-group? Because I can't see from the definition here what kind of elements it represents and how we can apply in mathematics this anti-ideal in this context.
Now, if you want to think about like whether semi-groups or groups or these things, we have lots of things in real life that they have this group structure or semi-group structure or monoid structures. And the ideal part, it's applicable. But in real life, there are lots of things that they resist. They don't have this intersection. Like there are sets that you feel like they don't belong to the semi-group. They are part of it, but the interaction, they resist the relation with the semi-group itself. So these things, we are studying them and we are calling them as anti-ideals.
Okay, so thank you very much. Some other question, remarks? If not, thanks once again.
Thank you. Thanks again for being here, and hopefully I can meet next in the coming 2 years in person this time.
Perfect. Thank you very much. So, and the session is over. Please enjoy the dinner and after dinner.